Hello participants, I invite you to lecture 49. This lecture is in continuation to my previous lecture on solar PV system for irrigation. This is part 2. Here we will emphasize how to integrate solar PV system with micro irrigation. So, in this particular lecture we will discuss about controller, we will discuss about pumping unit, we will discuss about the how to match and properly integrate solar PV system with micro irrigation system. So, a controller, it consists of a maximum power tracking point, inverter and variable frequency drive VFD. In short form we say VFD. The MPPT, that is a maximum power point tracking, maintains system operation at or near maximum available power. The power which we are getting from the solar panel. In this particular place which you are seeing that the power which is coming from the solar panel, then this power which we get, this power is DC. That DC is supposed to be converted to AC in order to operate the submersible pump. So, when we want to so this particular unit, it goes there. So, here we have got a VFD. A VFD regulates motor speed by varying the motor input frequency. An inverter converts direct current into alternate current, that is a AC current according to the type of load. So, means finally the energy it is supplied from the solar system to the pump, and then pumping system usually it consists of pump. This pump could be placed at the surface. So, in surface centrifugal pump or submersible pump, means it is placed below the ground level, and then the water is being withdrawn when there is a deeper depth of water available. So, variable speed pumps are powered by a synchronous motor or an electronic frequency converter that allows the pump to work under different angular velocities. And frequency converter can be considered as an inverter which is able to modulate the output signal to desired frequency and amplitude. Because what happened, that power supplied by the PV array is variable, means during daytime you may find that in the morning solar insolation is low and it increases. So, it increases means your solar insolation when it increases. So, energy available is also, so it is varying, and after and due to that is another part, and another one is that may be due to cloud also. So, such type of variable thing will happen, that will depending on the incoming radiation. So, power required by the pump can be modified by modifying the angular speed of the pump to match the incoming power. So, this is a very important thing, that matching of the pump required as per the demand, and then the how much power it is available, it is coming from the solar PV system. So, this matching is a very crucial and important. So, to select the most appropriate capacity of the pump for a particular application, the performance curve already we discussed in the pump class and previous lecture. There is a discharge head efficiency curve, and this curve this curve it is established between them of the pump provided by the manufacturer. So, pump manufacturer supplies this information, and this is this relationship is governed by the affinity laws that relate the shaft power. This is given here. This will relate with the shaft power, it will relate with the available head, it will relate with the discharge. So, and also with the speed, rotation speed. So, there is according to the affinity law, the means the pump discharge, that is the original discharge, ratio of original discharge to the pump discharge at a desired speed can be given by N2 by N1, where N2 and N2 is the pump speed, that is a desired pump speed to the original pump speed which is available with the manufacturer, and then it multiplied by the ratio of the desired means your head at a given speed N2 divided by the original head of the pump, and then this can further it can be given by the ratio of the square of their speed multiplied by the desired power to the means to the original power available in the pump. So, this is explained using the affinity law, and this relationship it is giving us valuable information while we are selecting the pump. This is the another important characteristic curve which you can see here, that how the head and discharge it varies for the pump when then the motor is the power it is supplied at the different frequencies, and when the pump is operating at different it has got different efficiency. So, you can see the typical curve which is available. This is the curve giving us the say 74.37% is the efficiency when let us say that a pump is delivering discharge, it is delivering discharge of 4 liter per second, and it is having the means it is then it has a the 100 meter head. So, 100 meter head, what is the appropriate efficiency? So, if I need a pump of this particular efficiency, accordingly what will be the power frequency requirement of the motor, that can be decided. Then on farm irrigation network, to select the operating point, that is the point which will be available from the curve we will get, and then that is a discharge head, that curve which I was telling you from this type of curve of the PV irrigation system. It is a function of power supplied by the PV plant, not only the simply taking the head discharge of the pump, but also one has to see the network system curve, irrigation network system curve. Now, two different cases can be distinguished depending on the type of irrigation system which we are using. Say case 1, which when we are telling when pump is operated to fill the tank which is at some certain elevation. So, here the one can find out what is the total head. So, total head H will be means from the curve we will be getting total head will be given by the change in the elevation. This is the difference in elevation plus the frictional head loss due to friction. So, this elevation difference one has to find out that when the pump is being used and how much head it will be required to fill the tank which is at some certain elevation. The another case is it is directly supplying water to the irrigation network, which is used in drip irrigation or sprinkler irrigation system. In case of drip irrigation system, it can be elevated case where the gravity system, after the water is filled in, then gravity system is used to operate the drip system, which is of low head drip system. But for larger system, when the system means where irrigation is to be given for a very large area, then it is directly the means irrigation system is directly connected with the pump. So, for sprinkler it requires normally a larger pressure, so pump is needed. So, the system curve can be calculated by updating up means by using the following relationship, where it says that the total head H is given by elevation difference plus head loss due to friction plus head required to operate the irrigation network, where drippers are there or sprinklers are micro sprinklers or the overhead sprinklers are there. So, how much pressure it requires to operate, plus frictional loss in the pipeline and all that take care of in by HF. So, there are other design parameters which needs to be considered while we are designing the system. Let us say then, so these are the following design steps one has to follow for sizing the pump PV system and then pumping system. So, first is the determine the water production goal. Water production goal means it is simply water requirement of the crop. So, we studied in the water requirement of crop a particular in the previous lectures, if you remember, how to estimate the evapotranspiration requirement of the crop by using different methods I discussed. So, pan evaporation method is one method, but here it is given highest water need. So, suppose we have got the crop which is grown, it is a perennial crop or it is a crop which is to be grown during summer month. So, water requirement during summer month, when it is during the peak period, that has to be taken into consideration. So, if the same crop is grown for last few years, so those data are to be analyzed, say, and then one can take 5 years recurrence interval, what is the maximum water or evapotranspiration needed by the crop during peak period, means when it is in the high demand period, that is to be taken in the design side. Then the another part is considering that what time of the day and what is the wattage available at that time. So, use the design month insolation, that is one sun, means the hours at one sun. Hours at one sun is, that is the for the design purpose it is taken as a 1000 watt per square meter for one solar day. So, that one sun hour, so that is the value which is considered in for the design purpose. So, this we are calculating Q, that is the design discharge will be daily demand divided by insolation multiplied by 60. So, this we will get the value of Q. Now, find the value of Q, that is a dynamic head versus discharge at particular discharge. So, this we will get this particular relationship, what is the value of H. So, we will find out the capacity of the desired head and for a given flow rate. So, we will get the value of how many number of modules it is needed, and these modules, when as I discussed, told you that they are given in series and parallel to get the maximum power. So, number of modules in series can be calculated by the pump voltage divided by the module voltage V. So, and when we are interested to find out the PV strings in parallel, this can be given by the pump input in watt divided by the number of modules in series multiplied by the module voltage, module current, and then derating factor. So, these values are available, how much it is there. So, one can find out the how much is the values which is for the in the parallel, and so that one can find out the number of strings in parallel, and then power input in kilowatt, it can be given by this also expression we gave you in when we were designing the sprinkler system, which is given by 9.8 multiplied by the total head, unit is in meter, and then the discharge in liter per second divided by overall efficiency. So, once the PV capacity is known, suitable controller of equal or greater size than pump rating can be selected, and also according to the maximum current and voltage of PV system and pump, the cable and switches, depending on the field requirement, they can be selected. Now, there are other expressions which are important when we are computing. So, solar PV system power calculation is made. So, we are calculating for the maximum power by using this expression, which is given by maximum power P max is equal to the nominal capacity of the PV system in kilowatt into 1 minus gamma, that is a temperature coefficient drop. So, this value is made available to us by the manufacturer, and then T cell one need to calculate minus 25. So, this particular equation it is developed for the set condition at 25 degrees Celsius. The operating cell temperature can be estimated by using this expression. So, T ambient for a given ambient temperature, NOCT, that is the nominal operating cell temperature, this also it is provided by the manufacturer, and so we will work out this value. So, we will work out this value, and this is for a particular time of the day. So, this we will work out, and G is the solar irradiance, this also for a particular time of the day. So, one can work out what is the P max available at in the particular period. Now, here we are integrating the system with the solar PV system with the micro irrigation system. So, this integration it involves that there is a you can see here the sun is the source of energy, it is supplying the solar energy, and then this particular the solar energy, it is generating energy, and that is in DC. So, we need to convert by using the VFD, that is variable frequency distributor. So, we are converting it. If the generated energy which we are generating, it is more than this, then it can be fed back to the grid supply. If it is more than the desired value, then it can be also stored separately. It can be stored separately, and then as and when it is needed during night time or any other time, this can be supplied, or when there is a say problem with there is a raining or some cloud condition exists, at that time this can be done. Now, then by using the VFD, we are supplying the power to the motor, and then the pump is supplying water to the irrigation system. So, pump is discharging. The interesting part here, it is that the power generated from the sun, it is a variable, and it is not fixed for the whole day period. So, during daytime diurnal period itself, you can see it is going peak, and initially it will be going slow, and then it will go to peak again, then again it will go down. So, the science involved are the main part it is involved. It is not simply direct coupling. One has to know that how the discharge means power available or discharge available from the pump, which will generate the pressure. That pressure matches with the requirement of the pressure, which when we are operating with the or connecting with the drip irrigation system or micro sprinkler system or sprinkler irrigation system, it will depend. So, this is where a important aspect is involved, how to use the available power or head pressure for operating the system, because you know the discharge from a drip emitter, discharge from a sprinkler system, it is a function of operating pressure. So, discharge will increase or decrease depending on the pressure available. We have installed SPV based micro irrigation system. This particular system is supported by Ministry of Agriculture and Farmers Welfare. Now, there are 16 panels, each panel is of 320 watt capacity vision, and then this system is a standalone system. It is a single axis sun tracking with grid storage arrangement. The total system, it converts total energy is of the order of 5.12 kilowatt power, and then the which is being used to operate 5 horsepower submersible pump, which is located at 30 meter below the ground level. The pump capacity as well as we have a arrangement for the data logging, which is being used by using the GPRS, where the data logging for the solar radiation, temperature, flow rate at every 3-minute interval is being monitored. The system this particular system was installed in December 2017. Now, strategies for integrating solar PV and micro irrigation system to regulate system and to optimize use of generated energy for irrigating the crop is to design more than one irrigation unit in the field. Means we need to see that whether we need to supply water for at one unit or more than one unit. So, whole farm can be divided into number of unit, so that the available system can be effectively utilized, and then whole energy which is available from the field, it can be used for irrigation, and then cost of the system can be also reduced. So, when farm is divided into the number of subunit greater than 1, the discharge and power needed to irrigate each unit can be obtained by dividing the maximum discharge and the maximum power by the number of subunit, and according to the power availability, these units can be irrigated. So, in this case, system can start irrigating with the shaft power, that is the NS, and time lower than when the only one subunit is considered. Two different strategies can be utilized. One strategy to irrigate with only one irrigation subunit in operation, or to irrigate with multiple irrigation subunits in operation, that is operated simultaneously. This is a typical, you can see how the solar insolation during daytime in different season it varies. So, you can see here this is the total sunshine hour, we are putting it say from 6:30 to means some places this it goes till late 7:30 or so in the evening time, but you can see the maximum power available is between 12 o'clock to 1 o'clock. So, this particular curve it is for winter where the minimum energy is available, and then solar energy is available, and then this is red curve which you see that is for the maximum. So, this is during summer month, and then the autumn and spring they are falling in between winter and during summer. So, this is a variable. So, solar insolation it varies. So, power availability will also vary, pump discharge will vary, that is where the important part is how to match this varying solar intensity with the pump part. So, this is the one layout it has been shown here. There is a field where the pump is located, and then from the pump the main line, and then there is a from the main sub main line is there, and then there are the sub main your manifold is that sub main is connected with the manifold, and then from the manifold the laterals are attached. So, this is one layout which is given here. So, means from D to C main pipeline, from C to B there is a sub main pipeline, and from B to A there is a manifold, and on this manifold laterals are attached. The another strategy means your sub mains are laid in this way, and on which the sub main means your laterals are attached. This is another strategy or layout is given that from the pump the main pipeline is attached, that D to C it is brought here, and then this is your main sub main pipeline, and then sub main manifold it is the length of the manifold is reduced, and then the length of lateral is increased. So, this would be the another way, and one has to find out the really economics and amount of the power it is being generated. So, this can be the another strategy. The third strategy layout it can be made that pump is this well source of well it is located somewhere in the middle, then from there the main line is connected, and from main the sub main and manifold sub main manifold it is there, and from there the laterals are connected. So, there can be the another strategy. So, there can be the different layout and strategy it can be made depending on the field requirement. Only thing that one has to see in all these units that head loss due to friction is minimum, and we are saving energy, so that the maximum means we can select the minimum number of panels, and we can economize the cost, and the pump will be also of lesser capacity, lesser horsepower. So, it will be also economical. So, there are several ways one can work out the economics part. A solar irrigation pump system method needs to take account of the fact that demand for irrigation system water will vary throughout the year. This is what you have seen from the graph which I was showing, that the demand will increase because the power supply will be also changed. So, peak demand during the irrigation system is often more than the twice the average demand. Yes, it is correct. This will depend upon the course the at what time of the season we are considering, and then at what growth stage we are considering. At the initial stage it is too low, and when it is in the peak demand stage, when it is a fully developed crop maturity stage, the demand will increase. This means that the solar pump for irrigation are underutilized for most of the time in a year. This is correct, that initial part it is less, but so attention should be paid to the system of irrigation water distribution and application to the crops. We need to see that if the demand is less, then we need to supply the power to the partly to the grid. The layout of the micro irrigation system consisting of number of subunits will play the key role in optimally selecting the operating PV energy. Irrigation pumps should minimize water losses. It should minimize water losses, power losses. So, this should be without imposing significant additional head on the irrigation pumping system, and it should be of low cost. It should be economical. This is our aim. So, to get more detail about this particular topic, how to integrate solar PV system with micro irrigation system, please refer these books. These are useful for your study. So, in this particular lecture, we discussed about power controller, we discussed about selection of the pump, we discussed about how to integrate micro irrigation system. There could be different strategy, there could be different the layout system. So, this way, and in the forthcoming lecture we have studied several formulae, there are several equations. So, let us means we will have the practical experience, and while we will calculate those values in the forthcoming lecture, that is tutorial 10. So, thank you very much.